Welcome everyone. Thank you very much for joining us for this public lecture. My name is Harriet Bredel. I'm the Exec Director here at the Keck Institute for Space Studies. We've got a number of people in the audience who are spending the week with us thinking about digital twins for solar system exploration. So we're really excited to have a number of fantastic people in town to focus on that topic. And one of which is an expert more on the earthbound side of things. And so we're really privileged to have Dev come and do a fantastic lecture for us this evening. So without further ado, before we dive in, I'm going to hand over to one of our fantastic KISS affiliates and graduate students in material science, Zach Ahmed, who is going to introduce Dev, and then we will kick off the lecture. So over to you. Thank you, Zach.
Hello, everybody. It's my pleasure to welcome Dr. Dev Neogi, the William Stamps Ferris Chair and Professor at the University of Texas, Austin, where he holds joint appointments in the Jackson School of Geosciences and the Cockrell School of Engineering. He's also a Professor Emeritus at Purdue University, where he served as Indiana State Climatologist and held faculty positions in agronomy and earth, atmospheric, and planetary sciences. He leads the Extreme Weather and Urban Sustainability, or Texas Lab, pretty neat name there, where his research focuses on the interactions between land-surface processes, urbanization, and atmospheric extremes. Dr. Neogi currently leads the Atmospheric Urban Digital Twin effort as part of the World Climate Research Program's Digital Earth Initiative, working to translate fundamental science into tools for climate-resilient systems. Today he joins us to share his insights in a talk titled, "What Makes a Model a Digital Twin? An atmospheric science-based perspective." Please join me in welcoming Dr. Dev Neogi.
Thank you. Thank you, Zach. Thank you, everyone. I'm really very happy to be here because this is a topic that we have all been talking about for a number of weeks now, and not just within the room, but also broadly speaking, as you look at what has been some of the agenda items that the administration has been putting out as priorities, AI, machine learning, digital twin has really become a part of a terminology which has been much broader than what it was perhaps, say, 2 or 3 years back. So what I'm going to be really talking about today is ask this question, is that we have, as a community, been very computationally savvy. We have been data generators, we have been working with database models, and we have been using data as a means to both develop empirical analysis as well as for developing predictive stuff. And now we have something which is a digital twin. So is digital twin simply a modified name? Is it the same thing? How do we know a model is a digital twin? That essentially starts becoming a question. And I want to acknowledge that I had really been educated by this very lovely set of people here, several of you who you might find in the audience. That's their digital twin there on the screen. And it has been a great conversation in terms of the context and ideas as to how you create models, data, twins, decisions, and stakeholders, and so forth. And in particular, I want to highlight the learning I had by having the initial short workshop where we had at least 3 of the speakers here, Terry, Carl, and we also had Erin talk about how you use concepts, ideas, and develop a concept of digital twin. As I was trying to get this picture for Terry, by the way, I realized he is a pretty well-known author outside science field. If those of you are not known, he does have a digital twin on Amazon that you should check out about the work he has been doing on science fiction. So it was really nice to know about that. So there has been ideas that have bounced, and these have all been in a context which have been on a much wider domain than what I have been used to. But there were several common features that have emerged. And before I forget, I want to acknowledge at the back the architect behind some of my thinking, Dr. Manmeet Singh, who is a distinguished researcher at the Jackson School of Geosciences, University of Texas, who is, so if you have any hard question, you don't ask there, you ask there. Yeah, easy questions I'll take, of course. I also want to acknowledge that what I'm going to be talking about relies a lot on a National Academy study that has come out on the foundational gaps and framework that has emerged for digital twins. And in particular, to my colleagues, Karen Wilcox, who led that National Academy study at Odin, and Ruby Loing and Shinye, they have been part of this initiative. We have been about a consortium for digital twin, and we have been having almost this bi-weekly meetings over a number of years in trying to build this idea and a community of what it means about a digital twin from different contexts, from geography, social science, DOE, and so forth that we have been working on. And as a part of that, we have been having community workshops where we have had community members from different disciplines come together, talk about this concept of atmospheric and urban digital twins. And there have been thematic workshops, just the two of them in the last year. We had one about building energy, for instance, how do you use the building energy science, and then the second one, which was more on the context of cities and how do you represent cities, and things like this might be of interest to the LA port area, for instance, that there might be interest and so forth. And so bringing in these perspectives from industry, from decision makers and so forth has been the way we are doing. So what this talk is that this is a really a high level overview about what a digital twin landscape is right now. And this is really an invitation for our continued dialogue on this topic of how do you define it, how do we build it, how do we create and adopt digital twins into the world, which looks that it is where we are going to be doing much more of digital twinning than we have in the last few years. What this talk is not is, as I was explaining to someone who is developing our biomedical digital twin in the audience, is that this is not about the nuances of the mathematics of how we are going to build a digital twin. We'll be more than happy to have that conversation. And nor is it perhaps going to be a very satisfying answer to the question I posed, what makes a model a digital twin, because it is a pretty open question, I would say. So what is a model is the first question I'm going to ask. And then the second question I'm going to ask is, are digital twins just a model with a new fancy name that has become the funding agency's favorite buzzword, and hence we are suddenly finding that there are more digital twins coming up? And so how do we then distinguish the two has been one of the things that has been, I think, in our minds. So model at a simplest level, and a lot of what examples I'm going to be covering are from my own point of view, which is as an atmospheric scientist, more so as a numerical weather prediction guy, where we are talking about models as a simplified representation, where we have many parameters, parameterizations, approximations all put together, and we are trying to predict something, we are diagnosing something for the real world. So it is a representation of system of processes. It's trying to represent some processes. It could be hydrology, it could be energy balance, it could be buildings, it could be the whole cloud convection processes, or it could be the aspect of systems that we are trying to see talk to each other, the hydrological system trying to talk with the cryospheric system, the atmospheric system, and so forth. So the integration that goes in within that Earth system modeling framework. And so that's essentially our context of a model when we say from an atmospheric perspective that this is what we mean. But broadly speaking, of course, models come, as you know, in many flavors. One of the most initial models that we all know of are the actual architectural kind of models or the physical models, where you could have a smaller scaled version of something that has been done as you do in an architectural world, or you could have, for instance, in fluid mechanics, we do wind tunnels or water tunnels, and where you have a scaled down version of those physical aspects. We could have mathematical and statistical models that we use a lot, whether it is for predicting air quality using statistical models, or whether it is in the context of trying to develop our first principle analysis by basis of what we do with, say, radiative transfers, or the assessments that we would do with turbulence, and so on and so forth. There are these analog models which we use, and this could be something like if a hurricane gets formed in the Gulf around a certain week in a year, then we know the expected location of landfall and how much it would rain. This climatology of rainfall, or also known as a clipper, is one of the persistence modeling system that is used by the National Hurricane Center, which actually behaves surprisingly well in terms of where and how it is going to rain and where the hurricane might go. The other one could be like when an El Nino event forms, depending on when an El Nino forms and what is its severity, you can predict some of the impacts that might occur. So this is an analog feature that people will be using in terms of developing a model of the system. We of course have our computational and simulation models. Some of the more computational ones that we have seen is that agent-based models, where people are trying to understand, say, the traffic flow patterns, or like how disease spreads when we were having COVID kind of scenarios where people were concerned about these kind of things, and we were doing those scenarios. And now, of course, we have this whole body of evidence now growing into the context of literature for machine learning and AI-based model, and I'll touch a little bit on that. And those are a different kind of animal to some extent, where many of the physics and dynamics constraints are sort of let loose, and we let that kind of vision communities work, or some of the computational communities work in transformers and diffusions and others, sort of help us do things which we were not been able to do with the physics and dynamics as we understand it. Then we of course have the conceptual models. I mean, the very classically things like how a monsoon system was formed, or how a convection is a hot tower, and how clouds were formed, or a hurricane. So these were conceptual ideas that got built up over a period of time, and we have several of those. And then finally, what we do in atmospheric sciences or earth sciences, the process scale modeling, trying to represent a process and then build up on that process and so forth. And so there are many, many such models that can be generated. But the important point here is that there cannot be a singular definition of what a model is, and there shouldn't be, about what is a model. And yet somehow we are looking to try and define digital twin, as if there is going to be this one beautiful explanation and definition that is going to satisfy us. So I just want to place that in context, that models come in different flavors, and we need to probably start thinking digital twins also come in different flavors, and it is totally okay that your digital twin will not be my twin in going forward. So what is a digital twin? Simply put, there are more than 100 definitions that you can find on a given topic of a digital twin. And many of them start with this notion. So there is this very nice, well-cited paper about digital twin paradigm that goes from the manufacturing community to the process-based community and so forth. And essentially it has things like what you can see, that is a virtual representation of physical system, and it is also something which will try to match between sensors, data, models. So it is a combination of certain things that it is trying to interconnect with each other. There will be a cyber part or a cyber physical part, where there might be sensors and Internet of Things kind of things, or what some people call edge computing kind of applications if you're in a physical environment, trying to put all that together. And that you could have something which could be in the context of how it can have a predictive aspect of building forward and so forth. So there have been many such elements of what it seems like there is a cyber part and there is a physical part, and there is some elements of some decisions that start coming into this. In fact, this concept of digital twin seems to have probably first time come up in the 1991 book on mirror worlds by David Geltner. And here he was talking about it may be possible that we are able to operate real world by just looking at our window on a computer and then manipulate some images, and that can help us manipulate the real world. And this kind of a mirroring approach has been one of the first contexts of what we are now calling a digital twin in the way we look at it in our day-to-day applications. In fact, the way we look at it, digital twins now more formally, I think there has been a product lifecycle management aspect, and Terry will probably talk more about it and how NASA uses it, is that how you can use it in the context of a real space and a virtual space in terms of looking at the risk assessment, in terms of looking at the uncertainty, and in sort of replacing the human as if you are in the car crash test, and how you can use a virtual instead to try and understand the impacts and uncertainties and so forth. So this is whole product lifecycle management has been something that has been an element of a digital twin. Then there have been series of papers that have sort of taken that conceptual idea into mirrored spaces, and this mirrored space models has been the one which you'll find in the literature sort of as the anchoring of digital twin before digital twin became more prominent into the literature today. And then, of course, in 2010 or so, John Vickers came up with this into a much more of a NASA-ish aspect of digital twins, that how you can use this for the development of physical and digital simulators for spacecrafts, what you can do in terms of creating the physical real-time checks in terms of the virtual digital flight leader and so forth, and many of the things that, for instance, this group has been talking about in this week and previously about the elements, the components, the cyber-physical systems, the decisions, the applications, all became part of this particular virtual digital fleet modeler, so to say, or what they call a digital twin, in terms of what has been the vision for how NASA could start using it in terms of its uncertainty, risk, and assessments that they would do. Parallelly, in the atmospheric world, we have been doing what we call OSSIs, or the observing systems simulation experiments, in which you already have a model, and it could be something for, say, a hurricane forecasting or a weather forecasting, and then now you have new data that is coming in from a potential satellite that is being launched, or a data set that might come in. And then if you take that particular data and then you do a data simulation on a nature run, and then you develop with that simulated observation what could be the value that comes up in terms of that new data, then you can come up with a better forecast and show the value and the verification of the processes. So OSSIs have been used as a means of a digital twin to augment the models, and then bringing in the satellite data, bringing in the predictive components together, and sort of creating a quasi-digital twin in terms of our Earth simulators and so forth. So if you look at the definitions, then we have an industry definition, which is like, say, what IBM has used for a system which is a physical objects with a link between real-time data, simulations, machine learning, and start putting this together. In fact, when IBM was trying to put some part of it for the Rio Olympics as part of its giant wall that they were trying to use, they were trying to create this as part of the digital city, and they started using this concept of a digital twin much more at that point in terms of how you could use it for the cities and digital mapping. NASA, the original one from the Gleason and Stargill, the 2012 paper, which is the digital twin paradigm for future NASA and US Air Force vehicles, essentially came up with a definition which says that digital twin is an integrated multi-scale probabilistic simulation. It has many built-in features, but what I found really interesting is that the link between models, sensors, history, and then sort of mirror concept that I was talking about that was used as a thing for digital twin coming in. And then it will be predictive. It will tell us a bit about what could be the mission life cycle and what could be its potential for success. What can it do in terms of anticipating and uncovering unknown issues that humans could not? And then what can it do in terms of mitigating and help self-heal? So it's a very ambitious plan that was laid out in the context of what a digital twin can do for a spacecraft in terms of how it would start building up this whole projection, prediction, and a mitigation approach that came in. Last year, NASIM, then the National Academies, collated this group, and this is the consensus report and a definition that has emerged from this group. That where a digital twin is now a set of virtual information that constructs mimic structures. It looks at the context behavior of natural engineering and social systems. That was the add-on, that there is a human component that has to be embedded in terms of how decisions have to be brought in. Because I'll come to the point that one of the critical factors that differs between a model and a digital twin is the engagement of humans. That without human, perhaps we are still dealing with models, and the more human engagement is part of the system, a digital twin starts becoming more alive into that whole setup. It should have a predictive ability, and they were very insistent that there has to be bidirectionality. If there is no bidirectionality, then it is not an well-designed digital twin. That means there has to be something that it is learning, and there is a human as well as some feedback that is going on in terms of making that model more adaptive and learning as it goes. So this predictive capability and the bidirectionality came up as two important things. And that was between the virtual representation and the physical counterpart. And then, of course, this whole issue of verification, validation, uncertainty that Amy can talk a lot about, I guess, and in terms of the whole aspects of ethics and security, which I'm going to highlight a bit more towards the end. So digital twin, they say, is much more than just a simulation and model. And so that sort of like makes it that, yes, we are talking about two different things. And that brings us back to the question that what would be then a digital twin, and how does a model not continue being a model but becomes a digital twin? If you look at the timeline as to how digital twins have evolved, you would probably find some of the foundational ideas in the early 60s and 70s, and then you had seen some of this industry adaptation with the Internet of Things in around early 2000, and then the term adopted by NASA in the 2010, 2012 timeframe, and then this whole standardization from the industry perspective through consortiums and energy and industry particles coming together and creating this digital twin framework. And now this whole growth with regards to what we see digital twins because of this big push with regards to AI and machine learning and computational and GPUs that are becoming available to us. Speaking of which, there are some very important changes that have been happening in the last 4 years or so in terms of the kind of tools and approaches that are available, starting with, say, the transformers or the generative adversarial networks, GANs, or what you might have with your good old CNNs, or what is now becoming everybody's flavor, the diffusion models, in terms of trying different kind of tools and techniques that might be used to train a model, use the data, use incomplete information, try to decipher into a much more larger data set, try to get a sense about uncertainties, and try to build something which is beyond what we are sensing. And so these have been some of the things that have really helped us in move the needle forward in terms of what we have with regards to digital twin. So what do we have in terms of atmospheric sciences that we can use? Over the dinner, I believe, or lunch yesterday, we had this conversation that the atmospheric scientists are lucky that we have hurricanes so often, or we have thunderstorms so often that we can test our models as against, where you have a spacecraft or a mission which takes many years. And so I'm going to be actually looking at what we have learned in terms of some of these models and then try to see what can be deciphered in the context of what becomes a characteristics or a theme associated with digital twin going forward. So from the meteorological or the earth science community, if you look at these examples of digital twin, the European Center has one of its most ambitious digital twin experiment with billions of euros going into it, called the Destination Earth or the Destiny model. And this Destination Earth is really like the hallmark, and I'm going to talk a bit more about it, as to what they say is a digital replica of the Earth system that will essentially do past, present, and future in terms of weather to climate, in terms of everything using AI and machine learning at unprecedented scales. NASA, through its white papers, has essentially been saying it will be a coupled data model system that will integrate satellite data, will have predictive capabilities, and simulate Earth processes and help manage natural hazards and climate risk. I'm sure now it will say weather risks. WMO has been highlighting this more in the context of a virtual system and developing decision support system with an impact-based forecasting. So each agency, depending on how they're using it, they have taken the digital twin concept and adhered it or melded it to their application and the core area. So this flexibility is what has been making digital twin something which has been very attractive for a large group of people and communities to start doing this work together. Speaking of digital twins and Destination Earth or Destiny. So Destiny is a very ambitious project, and they have kickstarted, so to say, in 23. They already have two platforms, which I'm going to show, one of which is this Destination Earth or Digital Twin for Climate Change Adaptation, which is taking the climate information and actually linking it with very local scale decisions that cities or communities or industries will have to make in terms of what they're trying to do to reduce their risk associated with hazards. And how can you actually help that translation of information, that transition of just something which what I call a U to U framework, making climate information useful to usable, has been one of the critical components of where digital twins start coming in terms of the applications that have come up in terms of, whether it's an on-demand forecasting or it is a multi-decadal projections at very high granularity that we did not have before. The other part that they have been very successfully deploying is what is a digital twin for extreme weather factors. So this could be for, say, a hurricane or a typhoon, or it could be for a fire, or it could be for a particular event that they might have, and then just trying to create this on-demand extreme weather output at a very high resolution using the capabilities that are available with AI and machine learning. And I'm going to show you how this is actually really revolutionizing the manner in which we can do some forecasting right now with some examples we have done with our group. So what else can we then do with a digital twin that we cannot do with a model? That has been the next question, because this also helps us understand the difference between the model and a digital twin. And the first one is that we have always been wanting to put something like cities into large-scale Earth system models. Cities, as we know, are extremely complicated, and yet the reality has been we have never been able to put cities in climate models or Earth system models because they take such a small footprint compared to a global footprint, even though the impact might be large. And so one of the challenges that the community has always had was introducing this climate information or weather information or hydrological information in the context of what can be done with cities and the many layers that associate in creating a cities. And so this bridging the scales across the models into what could be like a large scale 100 by 100 kilometer grid information to something which is required at a neighborhood scale, this kind of bridging has been very difficult to do if you're trying to do it with a computational model, because you'll have to nest a model, then nest another model, and then it becomes a models of model thing, and it's an extremely computationally cumbersome thing. And so how do you do this in a regular basis, in and out, that you can have the flexibility and ease has been more the challenge that we have been working with. So one example that we could see is that we could take a case of data sets from what we have from some of the satellite data sets and create the building height data sets. So we have this global building height data set that are available. Now this could be easy to say that, yeah, it's almost like a topography, but what is interesting about integrating this with a digital twin is that it is not just in the data, it is also providing the right set of parameters that actually talk to the model, because it's one thing to have data and then having it interface to a model with the right set of parameters that are required by the model. And so that becomes an example of a digital twin in terms of how you can use it into a global context with very limited data that you have. And so you can use it for developing things like a temperature simulations, which have the heat island built in, which we did not otherwise have the ability to do so. You can do things like thunderstorms, how they interact with cities, and how it rains more in one part of the city versus other part of the city, because now you have more of the blocking effect that is coming up from the morphology, and then you can have thermal comfort and so forth. It also allows us to breach the model physics, and by that I mean that here is an example of a campus, our UT Austin campus, and so this is a U-twin for University of Texas. And in this, what we are doing is essentially creating a twin for every building and then trying to understand what is the energy use, what is the temperature, what are the comfort level right now, and what it would be in future climates. And so this allows us to start coming up with which of them might need some retrofitting, which of them might be an infrastructure aspect that we need to start thinking about as an asset that needs some attention to. And so this kind of bringing information to a building scale has not been possible because we were constrained by our dynamics, the rules that we have with scales and so forth, but that was possible by using AI and machine learning and how, etc. We can talk more about it. Now, we can say we are doing this and this is what it looks like, but verifying this information against some dynamical model has always been a challenge. Because in the first place, we are using machine learning or these digital twins to come down to scales which we have not been able to observe. But then, how do you know that this is right? And so there was an opportunity that came up during the Summer Olympics where a group of weather service teams from, say, Meteor France, from Germany, Canada, UK Met Office, and our lab, we all started coming together, and our goal was that we will do the forecast using the AI-based system, and all other teams are doing it based on the traditional physics-based approach. And so this was a real-time blind forecasting that we are doing using AI versus a physics-based model that is going on. So here, for instance, Manmeet started with a team putting all this information together, training this with a data set. Our challenge was twofold. One is downscaling this information from a coarser resolution to a city scale. And second is making this temporally more attractive from 6 hourly to 1 hourly. So for that, we were trying to train this data over Paris, but we realized we didn't have much information available for Paris. So we had to train it over DC and then do some transference, and using the transference learning, apply it for Paris. So there were a lot of these uncertainties, but nonetheless, when we applied it, we find that these models, which are run with about, for a 24-hour run, they take about 2 hours, 150 minutes or so to try and develop a model forecast for a 24-hour. A AI-based model typically takes about 2 minutes to run. Of course, the training that was done on an H100 kind of a GPU had done for a considerable period of time, but once we had that database ready, running the model for a daily basis was a matter of few minutes. And this is what made it very attractive, and given as how we were able to still capture some of the diagonality and so on and so forth, was very interesting in terms of seeing the value of using machine learning or AI for this kind of a urban digital twin framework. In fact, we could in fact simulate what a marathon runner would feel on the day of marathon in terms of what it could be at a 2-meter resolution, heat and thermal stress that they would experience. Now, from a traditional model, this was not possible to do so if you're trying to do a forecast which is at a 2-meter by 2-meter resolution in terms of the winds, radiation, thermal speed that they would experience and so forth. And this was then used to make a decision whether they should prepone, postpone, or keep the marathon at the same time, because there were some options available in terms of how it could be used. And so this is the kind of capability that starts coming up once people have a digital twin that can be used. And so here's, for example, about what you could do and so forth. Now, it's not just pretty pictures. What you really start coming up with this combination of vision and machine learning and satellite data sets and the dynamics that you have is that even some incomplete information can be fused together, and you can then start taking information and create this extremely realistic. All of this is digital, by the way. This is computer generated, and this is available in terms of what you could look at in terms of what you could generate as a CGI graphics that could be used for input to the models. So once you have this information, so for instance in Paris you could go down and look at the lattice in terms of how a structure is, where the trees are, where that information is. This information starts becoming dynamic. So all you need is a small sample of data and then the rules, and then you can start amplifying, multiplying it, and then start creating this kind of a data set in terms of putting this whole global system of information that is not just photorealistic, but actually very computationally important, because it starts giving us data sets that are required for doing our predictive models. And those data sets could be things like what is a DEM, or what could be in terms of the height of certain obstruction, or what could be the rules by which you can map buildings in a given area, or what you could have in terms of how you want to set up some of the domain with data parsimony. Minimum data to give us the maximum output so that you can start creating this setup in terms of where you want to go with this kind of information and so forth. The other advantage when you have a digital twin is sensing the unsensed. And by that I mean, this is not nonsense actually, it's in the context that you can see building or you can see some surface, but we were just talking, in fact Krista and I, we were talking quite a bit as to how much we know about the buildings and urban, but we have so little understanding of what's in the subsurface. And how do you then do this? The same thing in terms of the insides. We have a lot of understanding about how we can map outside, but we don't know what is inside in terms of the buildings and so forth. So you can create these twins to try to get information about the unsensed environment with what you are sensing and try to create this very intelligent output in terms of the scenario. Now, I want to scale quickly to something else. And one of the things that we have is with regards to a creation of a data set that can then become a community data set for hurricanes and other things that we are doing. So here, for instance, this is Hurricane Beryl, which was, I think, heading for Austin per our initial physics-based models guidance. But when you started looking at the AI-based models, they were actually pulling it much away from Austin. And so this caught our eye. And this is an example about how you can use AI. And this was 5 days ahead than what a physics-based model actually told us. So the irritating part about the AI models is that you get the answer which looks right, but you cannot explain why it is right. And this has been a problem in terms of how you can then use this data set, because you don't even know whether this is going to be consistently, persistently right. And that has been one of the issues that we have. So combination of something that we can do with regards to physics-based approaches and also looking with what you can do with an AI-based approach and then developing this confidence has been one area where there has been a lot of growth with regards to how digital twins are being used right now. I think I should be closer. Yeah. The other area where digital twins are coming in are embedding them within physics-based models. And so you already have a very detailed physics-based models, and there are some modules or some parameters which are very time-consuming. So radiation transfer, for instance, in this particular scheme. And you could replace that entire physics-based approach by a digital twin or a machine learning-based approach and use that as an augmented digital twin kind of setup that goes in with that whole scenario. So in going with how you have creation of the setup. I'll just quickly move through and then go into the, so is digital twin a model? I think the answer is not. That digital twins could be a class of models, and what we know is that digital twins go beyond the model capabilities. They have a user-inspired and application-centric. They have a bidirectionality with updates, and they have a multi-scalar data option that are not necessarily constrained by just the physics that we know. What we still need to do is understand and benchmark them more. We still need to do a lot more in terms of the explainability from digital twins, because it might give us a right answer, but we don't know why. We need to understand the uncertainty propagation, and we need to understand and accept that there could be a variety of definitions for digital twins and use them rather than trying to have a single nice definition that goes for. So this is a quote I've heard often in our conversation, that digital twins are often like a low-cost insurance. It is attractive, but we can never really be sure it is going to be working when we really need it. And that is scary when you start thinking about it. So I will close up by saying there are 10 things that seem to emerge as the factors that define a digital twin. And the first is, at the first level, is that this is either an engineering replica or an engineering digital twin or a process-based replica. That is our first factor by which you can say this is a digital twin, and there are two communities that seem to be there. One trying to replicate engineering and another which is trying to replicate processes. Second, it builds on some elements of data. Without data or some data-driven approach, you are not creating a digital twin. You're just creating a model. Third, it needs to have the desired characteristics of some elements of learning. There has to be some adaptive learning. Somehow the model has to learn. How it does that, we have to figure that out, but there has to be a learning and self-generation of knowledge into that system. Fourth, it needs to have a stakeholder or a use-inspired, not user, use-inspired. So it could be between two models. Obviously, if there's a human involved, even better, and it can become much more interactive and attractive in terms of its success. But it has to have that bidirectionality and a stakeholder embedded. Fifth, it needs to be interoperable. You cannot create a digital twin that can only work a place and not have the ability to transfer it to someplace else. You need to create interoperability in terms of making it really a digital twin. Otherwise, you are really tying it as a decision tool. Fifth, it has to have an ability to integrate or benefit from AI and machine learning somehow. So the elements have to be designed in a way that as we move into the AI machine learning world, that it can benefit from it, and however that we are doing. And of course, the if-then scenario generation or the speeding up, making the models 1,000 times faster, 10,000 times faster, or their scales, which could be much, much, much finer, those are some of the areas where I think AI/ML starts coming in. Visualization seems to be one of the important aspects of a digital twin, that as we start looking at it, because that's how we are probably going to get something cognitive out of it, that we can start trusting, building our confidence in and using it. Modularity is a really important aspect of a digital twin, that you need to be able to add and pull things out without having to go to the drawing board again and again. Because the biggest challenge in a digital twin is training it. And once you have trained it, you need to have the ability to play around, break it, use it, build it, rather than having to go back again and create a new digital twin every time. Ninth, there is a necessary element of uncertainty and explainability, verification and validation that has to come in, because without that, digital twin is just going to be an attractive image creator and not a useful thing. And lastly, there is a very emergent issue of ethics as to how do we trust a digital twin versus a process-based model, and how do we then use it in terms of our decision making when we have to make a decision which we cannot explain why we did, other than the saying that the model said so. And this is going to be one of the challenges that we are going to face as we go away from physics that we understand, explain, and can suggest how we got the answer, than just relying on a digital twin in terms of anything that we'll be doing. So I think I'll end up there by saying that digital twins are not just a new term for a classical modeling framework. I hope I have been able to communicate that. I also hope that there's a communication that there's no single definition that we should be looking for. And it is okay to have multiple definitions, like hundreds of digital twin definitions that can emerge. Different digital twins seem to have some common attributes, and they all seem to have that feels like, works like, builds like, and behaves like features that we can all start agreeing and appreciating and using them. And this is a real and exciting avenue, because it will let us go boldly in things that we have not been able to sense, things that we have not been able to do, and somehow that apprehension that we would have about using it and breaking a system is really now possible. So I'll stop there and say thank you very much. I really appreciate the opportunity to talk to you. Thank you.
Thank you, Dr. Nyogi. Fantastic talk. We'll open for questions from the audience. Have anybody to start us off? Sure. Got one right here. Let me step up this way.
As I understand it, Singapore has one of the more advanced urban digital twins. Can you comment on what you know about it and how advanced or where they are in their overall life cycle of development?
Like similar to what you saw for Paris, in fact, Singapore's digital twin is probably one of the biggest efforts that are going on, where they're trying to put every data, Internet of Things into a digital framework. I know you're interested in ports and airports and so forth. Those are probably the first starting point. The critical infrastructures have been starting point where people have been just focusing on few areas, and that's where they went. Then the second approach has been that they went on governments and all the public data and then tried to together. So it is tying different subsets of things and then putting it all together has been the manner in which digital twins have been put together there right now for Singapore. But it's a great example of where it can actually have a country's digital twin. Yeah.
A question down here. If I can get you to pass this to the gentleman with that jacket.
Hi, Dev. So curious, one of the things that we've been looking at is, I would say instead of cheap insurance, I would say digital twins may be like very expensive insurance. You're still not going to sure if it's going to pay for itself. But in terms of investment perspective, is the juice worth the squeeze? Have you looked, or is there any data coming in that says, my indication is that digital twins are not going to be cheap, and that you need to do it deliberately, and you need to be willing to pay for it. But what is that magnitude? Because as you add more data, HPC comes into the equation, and then we really need to start using that as an evaluation criteria. But I haven't really seen any metrics or any data come out of that yet.
Yeah, no, that's a really good point. I mean, people say, oh, this model runs in 2 minutes. It is sort of like that Picasso example that it took me 50 years to come to this level. It is the training and the infrastructure that is required, that's non-trivial. It is actually a huge aspect. In fact, that 45-year reanalysis data that we have from GraphCast that we generated is for that kind of a purpose, that anyone who does not have access can use it. But to answer your question, is there any matrix out there right now? Answer is no, because we are sort of like in a data center mode. We just want to build it. We'll figure it out, how much it is costing, what it is going to do. But anytime when people are saying it saves time, it's saving resources, I think we have to look at the life cycle of that particular thing before we really say this cost us X amount. You might have more information. I would love to have that, yeah. But it is probably, I would say that for a project, if it is a 500K project, it's easy to say that there was a 10x initial investment that went in there, at least. So it was a 5 million that led us to that 500K kind of thing. Now, whether that sustains itself over a life cycle of 3 to 5 years in terms of the savings it could do, I don't know. But it is clearly, at least you need to have a 10x plus initial investment to get that kind of reduction in the discounts you would going forward.
Other questions? Okay. I saw the blue sweater first.
And he warned me he's going to have tomatoes. So.
No tomatoes. In the context of the ethics, it sort of reminds me of a more quantitative issue, which is the issue of robustness. And you didn't use that word anywhere in terms of how is it robust to errors in the models, to errors, to outlier observations, especially if it's going to be used for decision making. Do you want to comment on that at all?
Yep. We use validation. We don't believe in the robustness of our models. The black swan events, I'll give an example of, like some of the models that we tested were for a finite period. And so the question came up, can it predict things that it was not tested for? An extremely unusual event. And I make this example about a very heavy rain event or an extremely severe hurricane, which was not part of the training data set. Somehow, the models seem to have the awareness to predict that. So the more we use this for those extreme events, I think we are going to have more faith and believe that that particular model is robust enough. But it boils down to, again, having a metric, which is like, what is going to be our metric for validation? Is it going to be benchmarked against process-based model? Is it going to be benchmarked against some known data sets that we are able to replicate? I don't think the community has thus far come to that set of quantitative robustness that you meet this criteria like a Turing test, then your model is great. I don't think we have that yet. And that ethics issue comes up for the reason that, I'll speak this from a very simple example. The Austin, when we were getting Hurricane Beryl coming towards Austin, the emergency operations had been pulling up everything at the mayor's office. And we could see that our model was trying to show it is going westward. And so I called some people and say, looks like it is going to go west. But what do they do then? Do they just continue investing into that whole operation, or do they pull back? And what happens when you are much, much more sophisticated and expensive decisions that have to be taken, like for instance, a flight simulation path or something along those lines? How do you justify? I think we really, really need to have, when we are creating a digital twin, some critical benchmarks that need to be established and met as a criteria to say, this was met, hence, now we call it a usable digital twin. And I don't think we have that benchmark yet.
I have a question here.
Thank you, Dr. Nayogi. Just, in the comparison between digital twins and models, one of the characteristics, for example, for inverse models that we can scale up. To what extent do you think digital twins will help us in the future to scale up from small scales to larger scales to understand the generalized process?
I think, so I'll answer that in two ways. Our challenge has been scaled down, or creating a coarse resolution to high resolution. And it has a good ability to do that, as I showed you. Our second challenge has been to take incomplete information and create a much more complete picture. I think we have been able to see that it does a good job of that. Now, when we are trying to do the scale up aspect, which is like you have only limited information and you're sort of generalizing, I think there is a potential to think that this will happen. But it sort of goes back to the same issue I was talking about, the black swan event kind of thing, that here, except that now the domain is different. It is not in time, but in space, that you're trying to create something which is much beyond what it is said. But if you look at what I showed you for Paris, with the rules that were found with the arches, the trees and so forth, the rules of how the world at least behaves are structured in a very limited set of possible combinations. So at least from an Earth system perspective, there are finite number of, they may be million, they may be 10 million, but there are finite number of combinations that can help explain a scale-up capability. And I think the way we have the computational tools set up right now, I'm pretty confident that that is something that can be done.
All right, I think we are going to pause it here, but I see a couple of questions from our workshop participants. I encourage you to talk to Dev tomorrow during the workshop. Final round of applause. Thank you, Dev. That was a fantastic talk.